All right, in this video, I'm going to talk about support vector machines. Well, support vector machines are a class of supervised algorithms, supervised machine learning algorithms that are mostly used for classification. However, they are also capable to do regression for you. And the good thing about them is that they can achieve very high levels of accuracy with relatively low computation power, and they are very intuitive and easy to understand. Well, the objective of a support vector machine is to find a hyperplane in an n-dimensional space that best classifies the observation. And here, n is the number of features. Let me show you what this means with an example. So if you have a data set that only has one feature, say the age, and two classes, say whether the person is old or young, right? So you can have people ages, and depending on their age, you can classify them into young and old, here shown by the two colors blue and orange. In this space that is only having one dimension, the classifier is actually a point, something that is going to say anyone who is older than this certain age is going to be considered old, and otherwise is going to be considered young. Now, let's say that we have two dimensions, x1 and x2. Basically here, we have two features, and we have plotted our observations and used color codes in order to specify the group or the class that they belong to. Well, in this case, you can find a line that is of one dimension, basically a hyperplane, that goes through these observations and separates them into two classes. Anything below the line will be grouped in the blue class, whereas anything above the line will be grouped into the red class. Now, we can extend it to 3 dimensions, and there you will actually have a hyperplane, and there is no limit to the number of dimensions or the number of features that you can have. The only problem is that it is going to be very difficult for us to visualize. However, the SVM works perfectly fine as you increase the number of features. So you can generalize and say that with n features, the classifier is a hyperplane with n minus 1 dimensions. Now, very similar to the situation that we had with the OLS regression, we will quickly find that there are multiple lines that basically go through the observations that we have and can potentially separate our data into two classes perfectly fine, at least in the training data set. And then the question is, how are you going to find the best line? Or in other words, what is the criteria for choosing a classifier? So let's start with the very first basic concept, which we know as maximum margin classifier. The point that I want you to remember is that the maximum margin classifier is very different from support vector machines, but it is the beginning of the concept of support vector machine. So it is very important to understand exactly what a maximum margin classifier is. All we can say that in maximum margin classifier, we can find a hyperplane, or if you're talking about a 2 dimensions and 2 features data set, a line that has the maximum distance or margin from the observations in all cases. Well, if we can find that, then we have basically found our line. So in this case, you can say that there are multiple alternatives, and between the alternatives, the one that actually goes right in the middle would have the maximum distance from all the observations. In other words, this line is not a really good line because it's too close to the blue class, whereas the one that is right in the middle is the best one. And once we have found this line, we can say that anything that is below the line is going to be in the blue class, whereas anything that is above the line is going to be in the orange class. Now, let's see how it actually works. What is the mathematics behind it? Well, we can formally define the task of maximum margin classifier as classifying a set of observations into two classes based on n features. Well, we can also assume that if y is equal to 1, that is denoting the observations in one class, whereas where y is equal to -1, it is identifying the observations in the other class. All right. Now, if we have that, then we can find a hyperplane that perfectly separates the observations into two classes such that for observations that y is equal to 1, meaning that they are in, say, the first class, beta 0 plus beta 1 x1 all the way to beta n xn is going to be above 0, or for observations that are in the other class where y is -1, then this equation is going to have a value less than 0. And again, something that I want to remind you is that we are basically talking about this situation. So here, this is the formula of our line, our one-dimensional hyperplane, which is saying that beta 0 plus beta 1 x1 plus beta 2 x2. That is the formula. Now, if you plug in the values of any point and that ends up being above 0, you are basically referring to a point above this line. Therefore, that is in the orange area, and vice versa. If you plug in the values of any other point and that ends up being negative, you are basically talking about a point that is below that line. So that is how this is mathematically represented. So we are going to say that if point is in one class, say the class of y is equal to 1, if you plug the coordinates of that point into the formula of our hyperplane, then that would result in a positive value, whereas if the point is in the other class, if we put in or plug in the coordinates of that point into the formula of our hyperplane, that would give us a negative value, indicating that is in the other class, or basically it is below the hyperplane. Well, with the assumption of y equal to 1 for one class and y equal to -1 for the other class, we can summarize these two equations into one. We can write them as multiplication of y by the formula of hyperplane, and then we can say that this should be larger than 0. Now, let's see why is that. Well, for the observations where y is equal to 1, meaning that they are in our first class, we have this condition that when we plug in their coordinates into the formula of the hyperplane, the value should be positive, meaning that it should be above the hyperplane, right? So in that case, you can actually say that y multiplied by this value should be something that is greater than 0, right? Because 1 multiplied by something that is the value of the hyperplane should be larger than 0, and that is shown by the inequality here. Now, in the cases where y is -1 and this value should be negative, then we are basically saying that if you multiply two negative values, it is going to be positive, right? So you can say that the multiplication of y by the result of plugging in the coordinates of that potentially of that point into the hyperplane should be negative, and if you multiply two negative with each other, the results should be positive, and therefore it is what we have shown here. So once we have summarized the classification of the observations into the two groups using this one single formula, we can actually go and define the maximum margin classifier as following. So instead of saying that, we want the observations to be either above or below the hyperplane, we can say that we want their distance to be larger or equal than m, in which m is a positive value. right? So this is the distance, and what we want to do is to basically maximize the distance, right? So we have to figure out a way in which we can maximize the distance of all the observations from our hyperplane. So that is going to be a conditional maximization or optimization problem. Then the other condition that we are going to have here is to say that the sum of the beta j squares should be equal to 1. And the reason that we have this here is to give meaning to the second equation, and that is based on what I'm going to describe to you right now. So again, if you have the hyperplanes formula here, beta 0 plus beta 1 x1 plus beta 2 x2, and you want to calculate the distance of any point to that hyperplane and call it d, then the distance would be equal to beta 0 plus beta 1, and then instead of x1, you're going to put the coordinates of the first dimension. Here is x1, 0. And then instead of x2, you're going to put in the coordinates of the second dimension, which is x2, 0 here. And then divided by the sum of beta 1 square and beta 2 square. Okay, this is the formal formula for the distance between any point and any hyperplane. All right. Now, if the sum of beta 1 square and beta 2 square is actually equal to 1, then you can remove it from the denominator and say that the distance is going to be beta 0 plus beta 1 x1 plus beta 2 x2, right? So, and that is basically what we have here. If this condition is true, if the sum of the beta squares are actually equal to 1, then you can actually go ahead and say that this is the formula for distance. And what you're going to do here, the task here, is to maximize the distance of the hyperplane from all the points in our data set, regardless of the class that they are in. So that is the conditional or constraint maximization problem that we have to solve, and it's quite easy actually. You can use the Lagrange functions to solve this maximization problem. Now, let me show you visually how it works. Well, let's say that we have collected data on the number of hours that students have studied and also whether or not they passed the course. So here we have one feature and two classes. The feature is the number of hours studied, and the classes is whether they passed the course or not. We are going to show them with two colors, orange for the ones that passed the course and blue for the ones that failed the course. Well, here we can find a threshold. Here in this point is going to actually be a point that has the maximum distance from all the other observations in the data set, and that is the one that I have shown here. And we can actually show that that is going to be right in the middle, because the threshold that is placed at equal distance from all the points would have the highest distance from all the points. And this is basically our maximum margin classifier. So all is good now, but let's see what happens when we have some outliers in our data set. So in this example, suppose that there was a new student that was added to our class who, despite studying 70 hours, ended up failing the course. And that is going to be the new visualization of our data. So we're going to have this new student with the blue dot that has failed the course, despite the fact that the number of hours that he has studied is way closer to the students who have actually passed the course. In this case, the threshold is going to be moved to the right, and that is quite a dramatic change. In other words, the classifier is very sensitive to the outliers, and what happens is, because of that sensitivity, when we find the classifier using our training data set, we are not going to be able to do a good job on the testing data set. So if, for example, there was a person who had studied these many hours that I'm showing with this new larger orange line and had actually passed the course, our classifier is going to classify it as a person that has failed the course. Why? Because the value is less than or is to the left of the threshold. Therefore, the classifier is going to say that this observation belongs to the group of failed student. And it is basically doing a wrong classification. So how can we solve that? Well, we can allow for misclassification. What does it mean? It means that we go ahead and find another classifier. In this case, is actually called support vector classifier, and we are going to allow for some margin of error, meaning that, hey, we are going to choose this point as our classifier, despite the fact that we know in the training we are making a mistake, right? So this blue observation should have been classified as passed, but we are should have been classified as failed, but we are knowingly classifying as pass because it is within a margin of error, okay? So if we do that, then rather than having like a dot or in a two-dimensional space, imagine that you have a line, we are going to have a tube. It looks like a street, right? That you have the middle line and then you have two lanes to the right and the left. So the task here is to find the widest street or the widest tube that you can run across your observations in order to classify them into two groups while accepting some level of error in the training as a trade-off for higher performance when it comes to testing. And what I mean by that is that in this situation, while in testing, you are making an incorrect classification when it comes to testing, then you would be able to actually correctly classify this observation because it is to the right of your support vector classifier, and you would classify this person as someone who has passed the course, and that is correct. So although in training you are misclassifying this blue dot, in testing you're correctly classifying this orange dot. To put it formally, while the new line makes some mistakes on the training data, it will perform better on the testing data, and it basically may be worth to make a few mistakes in the training data in order to do a better job in the testing data. Now, the lingo here is that the observations on the edge are called the support vectors, and therefore the classification algorithm is called the support vector classifier. Now, the other point that I want you to pay a lot of attention to here, and that is very unique about the support vector classifier and support vector machines, is that only the observations at the edge are going to affect the position of the support vector classifier, meaning that if you come and add many other points to the left for the students who failed the course and many other points to the right for the students who passed the course, it is not going to affect the position of your classifier, right? The classifier is going to change only based on the changes of the observations to the at the margin, right? At the very edge of the two groups. Now, here, the million-dollar question is, okay, how do you decide what margin of error to allow your support vector classifier to have. Basically, how far away from the center line you would allow the margins to go, or how wide are you going to have for your street, right? That you're running through this, because these dotted lines could be way closer to the main middle line, or they could have been way farther away. Well, that is going to be decided based on cross-validation. And that is basically a tuning parameter for your support vector classifier. It gives you a lot of flexibility on determining that particular parameter and seeing how well your algorithm makes predictions. So that is up to you. But before I show you how you can actually go ahead and choose that tuning parameter, how you are basically going to find the best margins based on cross-validation, let me show you the mathematical optimization problem for support vector classifier, and then it would make it much easier to understand what the tuning parameter is and how the cross-validation works. Well, the formula is actually very similar to what we had for maximum margin classifier. So here, again, you have the distance, and you are going to maximize the distance subject to the constraint that the beta j's squared should be equal to 1, and the distance should be larger or equal than m. The difference here is that we are allowing some error. So we can say the distance should be larger or equal than m multiplied by 1 minus epsilon, in which epsilon is a non-negative value, larger or greater than 0, and the sum of the epsilons for all the observations in your data set should be less or equal than c. And depending on how you choose this c, how large you choose this c, you are allowing more errors, or you are widening the margins for your tube, or you are widening the street that you are running through your points. So you can imagine at the extreme where epsilon is chosen to be 0, you are allowing 0 misclassification, right? The margin is actually set equal to 0, and this will turn out to be the formula for the maximum margin classifier, because 1 minus 0 is equal to 1, and 1 multiplied by m is equal to m, right? Now, on the other hand, if you start gradually increasing the value of c such that the corresponding values of epsilons for the observations is going to be allowed to move away from 0 and become larger, you're actually moving the margins from the middle line to the right and to the left, allowing more misclassifications. Now the point is, okay, how are you going to choose C? What is the best value for the C? And I said that you would choose that based on cross-validation. So what does cross-validation mean? Suppose that you have a data set. I'm showing it demonstrating it by this. And usually you choose a proportion of your data set for training and another proportion for testing. So in this particular case, suppose that we chose the orange part for training and the blue part for testing. The point is that you do not necessarily have to choose these specific observations for training. You could have chosen other observations, but once you choose a specific set of observations for your training, you can have a particular accuracy measure. And then if you choose another set of observations, you say that here you're again going to choose 75% your observation for training, but they are going to be a different set of 75% of the observations, and you're going to choose 25% for testing, but they are going to be a different set of observation for testing. That will give you another accuracy measure, and you can continue doing it depending on how many folds you are going to create in your data set. In this case, I'm going to say that it is a 4-fold cross-validation. So I am going to choose 4 different sets of training and testing, and I am going to calculate 4 different accuracy measures, and then I am going to find a way to summarize all of these accuracy measures together. In this case, I take their average, and that would be my overall accuracy measure. So this is how the cross-validation works. In order to choose the value of C, the tuning parameters, what we are going to do is that we are going to choose a random value and then do cross-validation, meaning that given that particular value of C, we will see how well our model does overall, right? Meaning that how well our model does when we choose many different combinations of training and testing data sets and calculate an overall accuracy for the performance of our model when it comes to testing, given that value of C, right? We record that, and then we are going to choose another value of C and see how well the model does, again, overall, based on different combination of training and testing of the data set. And we continue doing that, and we continue calculating the overall accuracy measure and recording that, and then we basically going to see, okay, what is the value of C that is going to give us the best performance. All right, these support vector classifiers work very well when you can find a straight line or a hyperplane or a point that can go through all the lines and very cleanly classify them into 2 classes. However, that is not always the case. There are many situations in the real world where you cannot have a linear line separating the observations. This is an example, right? So you can have a situation where you want to classify patients into the ones that got better after taking a drug or did not get better after taking a drug. So there you have 2 classes, got treated or not, and the features that you have is the amount of dosage, basically the dosage of a treatment that they receive. And there are many cases where if they've received less than a certain dosage, they wouldn't show any results. And there is a range of dosage for that drug that if they take it, they would do better, and anything more than that would actually adversely affect their situation, right? So you're going to have a situation where only between a minimum and maximum of dosage, you will see positive reactions to the drug, and anything less or anything more does not work, right? So in that case, it's very difficult to come up with one point that you can say anything less than this or anything more than this is going to be in either of the classes. Here is the 2-dimensional example. Here, you can see that if you have 2 features and then the classes are with the blue dots and the red crosses, it is impossible to find a line that can classify these observations appropriately, right? So what is the trick? And actually, the best classifier is something that resembles an oval or like a circle, right? It is completely nonlinear, and the question is, how are we going to find that? Well, if we can add a new feature based on a combination or polynomials of other features, say x1 squared or x1 multiplied by x2, then we can move this from a two-dimensional space into a three-dimensional space like this, and then run a hyperplane that perfectly separates the blue dots from the red crosses. Here is a visual example of it. I took this from the Tours Data Science website. You can see the link below if you want to read the article yourself. But if we have a two-dimensional space, we have features x1 and x2, and these are the groups. In the middle, we have the red group, and all around it, we have the blue group. We cannot separate them. However, if we come up with a third dimension, let's say based on x1 multiplied by x2, then we can bring the red dots lower and then run a hyperplane right in the middle in a three-dimensional space here, and basically separate these two classes quite perfectly. So that would be the nonlinear support vector classifiers that we have. However, as you can imagine, adding new features to the model can get quickly out of hand, especially if you already have many features, right? So remember, we said that we are not limited to 2 or 3 features. You can have many features. And if you have many features and it is impossible for you to classify, to find a linear classifier, and you want to come up with different polynomials of already high number of features that you have, your model will get out of hand and it becomes computationally very inefficient. So how are you going to deal with that? Well, there is a very neat and elegant mathematical trick called the kernel trick, which works like magic. And basically what it does is that it allows you to basically do the separations as if you have added the polynomials without actually doing them, right? That is the best way that I can describe the kernel trick. And the mathematics behind it are, quite complicated. I will link to a video that discusses the kernel trick, so you can watch it on yourself. But it is not within the domain of this video, so I'm not going to talk about it, but that is basically what the support vector machines are going to do. They are going to use the kernel trick in order to do the classification for classes that are not separable from each other using a linear classification.